All right, hello everyone. Thank you so much for joining. So what you have up here is the query processing program manager team. So the three of us, my name is Joe Sack. I'm program manager. We have Shreya and Kevin, and they'll introduce themselves a little bit more. The three of us, we work with the query processing engineering team for both SQL Server and Azure SQL Database. So everything we're about to describe today is applicable to both worlds, and may even expand beyond that as well. In terms of the subject matter, so we're going to start off with Shreya talking about graph. So we added graph in SQL Server 2017 and in Azure SQL Database. Just a quick show of hands, how many folks have had a chance to work with graph in SQL Server? Okay, good. So one hand, so there are a lot of people this will be new. And then we'll cover adaptive query processing. So this is a set of features, a new feature family introduced in SQL Server 2017. And the essence of it is you should just be able to have performance improve based on runtime characteristics. And everything that you're going to learn about today is actually a good baseline for what's coming up next in the future. So living in a cloud world, we're able to get innovations out there more quickly. So even if you're familiar with some of the things that we cover today, it's good to have a solid baseline because we're building on that over the next year, and we'll talk just a little bit about that at the end. All right, so with that, Shreya. Okay.
All right. My name is Shreya Verma. I'm a program manager with the SQL Server and Azure SQL Database team, and currently focusing on the graph processing features that we introduced with SQL Server 2017, and they are also available on Azure SQL Database. And today, I'll just give you an introduction of what the features are, what a graph database means, and then I'll show you a quick demo of what you can do with graph processing features in SQL Server. All right, so how many of you here know what is a graph database? All right, quite a few. But just to bring everyone on the same page, I'll just start with what a graph database is. And a graph database is nothing but a collection of nodes and entities, nodes and edges. Nodes represent your entities and edges represent relationships. And you might ask, so what is different from a relational database then? Because in a relational database, tables represent entities and foreign key represent relationships. So the difference is in a graph database, an edge or a relationship can flexibly connect many nodes to many other nodes in your database. For example, if you have a Facebook-like graph and you have person node and a likes edge, you can use the likes edge to connect person to another person. That means a person likes a person. Or you can use the same likes edge to connect a person to a restaurant or an organization. So it's heterogeneously connecting different type of nodes to each other. And edges are all, you can easily model many-to-many relationships using these edges, as opposed to foreign key relationships, which let you model one-to-many relationships in a relational database. And graph databases generally also give you easy or regular expression-based query language to easily write your traversal queries or navigation queries. And they support both OLTP and OLAP, just like relational databases. So why are we doing this inside SQL Server? And why are we not building a new engine altogether? And the reason is that we talked to several customers before we build these features in SQL Server, and all of them unanimously said that we want something on the same platform so that we don't have to perform expensive ETL operations. We don't have to pay for separate licensing keys, and we could do it all on a same platform. And then we thought that we are a mature product. SQL Server and relational databases in general are a mature product. We have seen 40+ years of industry and academic research. We have a mature tooling and a mature ecosystem, and a lot of community support from the community. And we are trusted. Millions of enterprise customers, they trust us with their data. They use us for mission-critical applications. And you can build both on-prem, cloud, and hybrid applications if you are using SQL Server and Graph on SQL Server or Azure SQL Database. And this is, again, all backed by research. It is not out of the blue. There is enough research that now proves that relational databases are capable of doing graph processing queries at par with dedicated graph databases, or even better in some cases. All right, so with that, now let's find out what's new in SQL Server 2017 and Azure SQL Database. You can now create a graph, which is a collection of nodes and edges. We represent or we model nodes and edges in the database as tables. So when you create a node type, like let's say person node type, you will be actually creating a node table. And if you create an edge type, you will be creating an edge table. And every row in that table represents a node or an edge in your database. To support creation of graph and to support querying or traversal queries in the graph, we have introduced some DDL extension and query language extensions, particularly the match predicate that lets you write your navigation queries. And with all these, you just get the tooling and ecosystem that you've been using with SQL Server, and you would just use the same query language and same tools for the new features. You don't have to learn a new ecosystem, or you don't have to learn new query language. This, like I said, this is completely integrated inside the SQL Server engine. So tools like SSMS, backup and restore, import, export, everything just works out of the box. Your queries can now join your relational and graph tables to each other. So let's say if you have your relational schema and your graph schema in the same database, your queries will be able to join them together for any reporting purposes that you might need. Along with that, all the other cutting edge technologies that SQL Server provides, like column store indexes, machine learning using R and Python, HA, everything is supported on the graph features. So you get high availability and everything out of the box for graph. We support all the security and compliance features, so dynamic data masking, row-level security, you just get it out of the box for your graph schema or graph tables too. And this is available on SQL Server on Linux as well. So let's see how you will create a node, or what the DDL extensions look like in the graph database. So if you want to create a node, you will create a table. All data types are supported. All indexes are supported, all constraints are supported, and you just add as node in the end to your create table statement while creating a node table. Now you may ask, if this is just a table, why are we creating this different type of table? Why are we adding this as node in the end and not just create a regular table? So when you create a node table, or when you create a table using as node, what happens is, along with the user-defined columns that you have created on your table, we create one implicit column on the node table. It's called $node_ID, which is a unique identifier for every node in your database. And it's a computed column and a combination of two values, your object ID and an internally generated sequence value or identity value. And it's stored as a big int on the disk, but it's a computed value, and if you select from the table, you see this JSON string here, which just tells you that this is a node table, and the schema is DBO, and table name is customers, and then the internal ID for that. And if you export it using, let's say, import-export in form of CSVs, you will get these JSON values out, and you can change the table name there, just in case if you want to import that data into a different table in a different database. And if you don't create, when you create this node table, we create an implicit index on the $node_ID column, a unique non-clustered index on this column. If you create a unique index of your own on this column, we don't create that implicit index, but if the user did not specify any indexes, then we add an implicit index there, which we use later on for faster traversals. Here, yes?
In this example, you implicitly imply customer ID to be your primary key, because that's in the calculated result, the calculated column as the supposed identifier of the row.
The question is, did you want to create customer ID as the primary key for this table? There is already a unique identifier, so why should I create my own primary key, right? Is that the question?
No, I get it.
So the reason is that you can have your own primary keys also on the table. We don't stop the users from creating their own primary keys. You can actually link another table to this using primary key foreign key relationships. That is also possible. We just create these node IDs for internal purposes, and these are unique identifiers. And if you want to use these node IDs in the where clause as predicates, we will recommend that you use your own keys for that purpose and not use the node ID, because it's a computed column, it's JSON every time it is computed, so performance might suffer because of that. Now let's look at how you will create an edge. Again, it's just like creating a table. You add as edge in the end. All type of data types are supported, all type of constraints are supported, all type of indexes are supported, including the clustered column store and non-clustered column store indexes. An edge table may or may not have any user-defined attributes. For example, the friend of edge here does not have any user-defined attributes, and that's allowed. But when you create an edge table, we create 3 implicit columns on that edge, along with the user-defined attributes that you have specified. And these columns are namely $edge_ID, which is the unique identifier for every edge or each edge in the database, $from_ID and $to_ID, which hold the node IDs for the nodes that a given edge is connecting. For example, if you notice here, when we created the bot edge or friend of edge, we never specified the type of nodes or the nodes that these edges are going to connect to each other. It's only when you insert data into an edge table, you insert the values for $from_ID and $to_ID, which tell the engine which nodes this edge is connecting. This allows the edges in SQL Graph to heterogeneously connect any node to any other node in the database. So you could basically just create one edge, call it my edge in your graph, and just use that edge to connect every other node in your database and not have different type of edges. Yes? I'm sorry. Right. 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 So the question is, how did you get the values for customer ID and stock item ID there, right? So on the next slide, I'll show you how you'll insert the data, and that's when we'll discuss how we get that. So this one just shows that the bot edge is connecting customers to stock items, and it shows that customers bought stock items. So from ID becomes the node ID of the customer, and to ID becomes the node ID of the stock item. Now let's see how we got those values there, right? So while we insert the data, inserting into a node is very straightforward. You'll just insert like inserting into a regular table. You specify your insert statement, the table that you want to insert in, the attribute names that you want to insert the values for, and then your either a select or directly the variables. But when you are inserting into an edge table, along with the user-defined attributes that you have on your edge, you now have to take care of inserting values for $from_ID and $to_ID, which are the node IDs for the nodes that you're trying to connect using this edge. So in this example, we are trying to connect customer to stock item using bot edge. So the bot edge specifies that customer bought a stock item. So we start from customer and we go to stock item. So our from ID becomes customer's node ID, and our to ID becomes stock item's node ID. And then in this example, I just got the node ID values from other tables in the database where the customer ID on my customer table matched this variable, and the stock item ID on the stock item table matched this another variable. Does that answer your question? All right. Moving on, let's look at the match predicate that we have introduced. Match supports or helps multi-hop navigation. It supports a join-free syntax for navigation through your graph. And it uses our ASCII art style syntax for graph traversal. So this is how your query or a traversal query will look like. In this query, we are trying to find all the customers who have bought a stock item, and the stock item being white chocolate snowballs. We are filtering the stock item name there, right? And if you look at the match predicate there, what we are trying to do is we are trying to find customers who bought stock items. So we are going from customer to a stock item via the bought edge. So anything that appears at the two ends of the arrow there in match, those are node tables, those are your node tables. And anything that appears in the parenthesis in the match is your edge table. So you are going from a node to another node via an edge. And you always go from one node to another node via an edge. You cannot directly go from a node to another node. And the arrow or the direction of the arrow that you see there is the direction of the edge that you have specified. So if you remember when we inserted values in the bought edge, our from ID was customers and then our to ID was stock item. So we were going from customer to stock item, and that's what we are doing here in our example in this query. We are going from customer to stock item. Now I'm going to show you a quick demo of these features or the syntax. And for that, we are going to use this product recommendation scenario. We start from a customer, and we assume that customer bought a stock item, and it was supplied by a supplier, let's say. And the supplier was from a location, and the customer is also from a location, and then customer can be friend of another customer. So let's say I'm using some kind of social media marketing for which I want to send ads to top influencers in my graph, to friends of top influencers in my graph. So for that, I maintain some social media data. All right, so now in this scenario, this is a very straightforward small schema, can be easily implemented in relational approach. And if in this scenario, I want to build a recommendation engine for people, for the scenario where people who bought this also bought this kind of query. If you go on Amazon.com or Walmart.com, if you buy something, they tell you in the bottom, people who bought this, they also bought this. So you might be interested in buying these other items as well. So if I want to build a recommendation engine like that, using this simple schema, using a relational approach, the query will look something like this. I have my current user who is buying the product and their customer ID and the stock item that they are buying. From there, I find out other users who have bought the same stock item that this current customer is buying. After that, I find out the other items that these other users have bought. And then finally, when I have the list of other items, I make recommendations to my current user. Not a very easy query to write, not very easy to extend, and not very easy to maintain in future. Right? Now let's see how this query will look when you implement it using the graph approach. And the query will look something like this. This is our recommendation query. And now let's try to understand what the match clause is doing there. So what we do is we try to identify all the customers who have bought this item. This item being white chocolate snowballs, right? So we get a list of all the people who have bought white chocolate snowballs. Then from there, once we have a list of all the customers, we try to other items that these customers have bought. Could be something else, right? And once we have that list, we filter out our current customer because they are already buying this item and they might have bought other items. We don't want to recommend those items to them. And we also filter out white chocolate snowballs, which was the item that they were buying. So we don't want to recommend the same item again. And then the remaining list that we get, we make that as a recommendation list to our customer. Right? So the query becomes like this. It looks like this. Now let's see a quick demo of this query here. All right. So here I have a simple match query which we just saw where we are trying to find all the customers who bought a stock item. And when we run this, we get a list of all the customers, right? A simple match one where we go from one node to another node via an edge. Okay? And then here we have our recommendation query. And we run that. And we get a list of other items that other people have bought and the number of times it was purchased with this query. And we can make these recommendations. I have a top 10 here, so we get a list of top 10. If you remove that, you'll get a bigger list. And then you'll say that this is all fine. I mean, I can do this match and it looks good. But what about if I want to do arbitrary number of traversals in my graph? Let's say if I want to find in my graph, I want to find me friends who are 1 to 5 hops away from me or 1 to 10 hops away from me. How do I do that using this new match syntax? Then the answer is that in the first version or in this release, the match syntax does not support arbitrary length of traversals in the graph. But there is a workaround that we suggest to our customers if they have that kind of scenario. And for that, they can write a recursive CTE which uses match and then traverses recursively through your graph. And in the example here, I'm going to try to find friends of customer 1 to 3 hops away, because my max hop value is 3 here. If I set it to 5 or 10, I'll get customers 1 to 5 hops away or 1 to 10 hops away. And let's run this query and see what are the results. All right, so when I run this query, it tells me people who are 1 hop away from Tailspin Toys, and then people who are 2 hop away or 3 hop away, and so forth, right? So I find people who are 1 to 3 hops away from this person in the graph. So if I want to run some, like I said, social media marketing campaign, I can run this, find the people who are connected to my top influencers, and then from there send them that campaign or advertisement. And what if, you'll ask, what if I want to write a shortest path query? Like I know a couple of top influencers for my product on social media. Now I want to see how they are connected to each other, and if that connection affects my marketing in some way, right? I want to research that area. So for that, you will want to write a shortest path query to find how these two people are connected to each other and what is the shortest path that connects them to each other. And again, shortest path we don't provide an implicit function for that in the engine in the first release. But you can write this workaround to calculate the shortest path. This uses a T-SQL loop workaround. It is a naive implementation or a basic implementation of Dijkstra's breadth-first search algorithm. And let's run this query, and then I'll explain you how this works. And if we run this query, we see I'm trying to find the shortest path between David and Emma here, and we see that David and Emma are connected to each other by 4 hops. And this is the path through which David can reach Emma, right, if he wants to. I don't know if you guys are able to see here. Right? Okay. So what it is doing is it basically finds the first level friends of David through this match. And after it finds the first level friends, it tries to find if Emma is there in those first level friends. And if Emma is not there, then it goes ahead and tries to find the second level or the first level friends for these people that it found in first level, and stores the result in a temporary table, and it keeps going until it finds Emma. And as soon as Emma is found, this filter here actually is for that. As soon as Emma is found, we quit and we return the results to the user. And that's how a shortest path query can be implemented. All right, now, all these demos, by the way, are in the resources slide later on, so you can have access to them on GitHub. You can download them and try them. All right. Now, after I show this syntax to customers and people, usually they ask me, okay, if match is going to make my life so easy, should I just stop using relational and start using the graph approach? And I say no. I mean, there's nothing that a graph database can help you solve that a relational database cannot. And we just showed you here, the recommendation query, you can write it using the relational approach. You can write it using the graph approach. It's just that in some scenarios where relationship traversals is the prime focus of your application, or you have attributes associated to your relationship also, or relationships are the center stage for your application, then you might want to consider the graph approach, because it will make your code simple, intuitive, and easy to maintain in future. So that's something that you can do. And here are some scenarios that we have seen people using graph databases for. Recommendation systems that I just showed you, fraud detection in banking and insurance and online shopping, where people are naturally connected to each other. So if you want to find fraud rings or something like that, you want to identify the links between the people or the hidden connections between the people. And for that, graph databases really work well in those kind of scenarios. Content management or bill of materials, again, are hierarchical data. They have hierarchical data where you have hierarchy of contents or a hierarchy of products that make up a product finally. And your queries will typically traverse the hierarchy top down or bottom up, and these traversal queries become easier using the graph database and easy to express also. So people are turning towards graph databases for that. And CRM for sales or marketing, where it is naturally a graph of people connected to each other and opportunities and accounts. And let's say people want to find the shortest path between two people who are working on a similar project or a similar account or opportunity. In those kind of scenarios, graph databases shine. All right, with that, I'll hand it over to Joe for intelligent query processing.
Sound check. Can you guys hear me okay? Great. How many developers in the room? Okay, good. All right, so I've been working with SQL Server since '99, and a lot of that time has been spent doing performance tuning. And whenever I have query is slow kind of scenarios, recommendations around what to look at have always revolved around two things over the years. First thing is weights and queues methodology, was something I've been using for years. And then the second is what we're going to discuss here, which is just the nature of cardinality estimation. So if this begins to sound a little bit esoteric, there are practical applications from just a pure query tuning perspective. So we'll go through that. Now, 2017, so last year, we introduced a new feature family. You might have noticed that the query processing aspect of SQL Server and Azure SQL Database has been relatively quiet, and we've had this renaissance of development over the last couple of years. We're going to have more to announce over the next year as well. And we introduced a new feature family called Adaptive Query Processing, and the idea is that we can't always make good predictions around whether or not the plan we've put together is going to perform well. And sometimes when we have to make guesses or we have to make adjustments to our assumptions, adaptive query processing allows us to adapt in real time based on runtime conditions. We'll go through each one of these features. Notice the question mark there. I include this as a placeholder that this is just the beginning. So we're laying the base for a set of innovations, and understanding how these work will be helpful for you down the road as well for what we are going to be introducing next. So you all willingly came into a query processing session, so I have to subject you a little bit to query processing mechanics. And in terms of query processing, I have a query, let's say I'm selecting from a table, select from order table, where product ID equals 10. All right. What happens? We submit that query to SQL Server or Azure SQL Database. What we'll do is we'll take the query, we'll take the text, we'll parse it, we'll potentially do transformations. So we'll potentially rearrange some things, remove contradictions, simplify the query where we can. And then we get to a very crucial stage, so cardinality estimation. So if I'm selecting from an orders table where product ID equals 10, there's a few questions we have around the number of anticipated rows. How many rows in the orders table have that product ID of 10? We have to estimate, and that's the actual row count flow that impacts the kind of plan that we create. So let's say I estimate one row. I say, you know what, there's only a match on one row, and we base this estimate on the statistics associated with the product ID. So we go ahead and cost the plan. This is all happening under the covers, so we have an idea of row flow based on the query that you just submitted. We start costing alternatives, so there's different things we can do. We have different join algorithms. We have different ways that we can aggregate. We have order of operations. So the query optimizer, the goal is let's get a good enough running plan to be created fast enough where it's worth it and doesn't outweigh the actual waiting forever to get the perfect plan. So we cost different alternatives, and then we ultimately select the one with the lowest cost, and that's what gets cached in memory. Now, if I'm executing that query for the first time, again, the select from orders where product ID equals 10, and once we've cached the query, it's the initial compilation, we'll go ahead and use that plan based on the match to that text. We'll pull it from the cache, then we'll get ready to actually execute, and at this point, we will pull the memory we might need if we have operations for that particular select that require memory. We'll look at degree of parallelism, and we'll go ahead and execute according to that plan. Now, what can go wrong? All right. Well, what if I get the estimate wrong? So select star from orders where product ID equals 10, and I estimate 1 row, but I got 1,000,000 rows. Prior to adaptive query processing, it's tough. You have this plan that's cached. If I have a bad estimate, this is what we're going to use to do the end-to-end estimation. So we're not going to change our assumptions. We're still going to use the 1-row assumptions through the end of the execution, and if performance suffers, so be it. All right, we don't have any mechanisms leading up to 2017 that allowed us to adapt. Any questions on that so far? This is yeah.
Whether query is chargeable, that's in the cardinality estimation.
So the question is where the query is chargeable. So if you have a predicate that has a supporting index that can then be used based on that predicate. So let's take the example of product ID equals 10. If I have an index on product ID, that means that I have an index, and I also have statistics associated with that index, and those statistics ideally show a data distribution that reflects the value that there is 1 row or there's 1,000,000 rows. Okay. So why would this be wrong? Why would we show 1, but we actually have 1,000,000? And this is where the developer skills of query tuning really come into play, because there's lots of different reasons why this can happen, and being able to pinpoint it quickly is definitely helpful, especially when you're in a time crunch and have to optimize on the fly. So common reasons. Your statistics are missing. So I don't have any statistics on product ID. I have to make a guess. The optimizer doesn't have an index. It doesn't have stats. Let's say you've disabled auto creation of stats. So optimizer has to just make a guess. So we have different fixed guesses in absence of that information. Stale. Let's say you have so much throughput, you have an order system, and you happen to have 1,000,000 products that just got purchased recently, but they're not reflected in the statistics. So when you execute that query, we're dealing with old assumptions. Also sampling rate. The bigger the table, the more jagged the data distributions. So meaning maybe I have product ID 1 has 1 row, product ID 10 has 1,000,000 rows, and it goes up and down and up and down. The more jagged the distribution, we might miss interesting distributions that would be helpful for query performance. But the fact that we don't have it reflected in our statistics, we have a plan that doesn't reflect reality. Bad parameter sensitivity, or parameter sniffing is the common term. How many folks have heard of this? Parameters, okay, good. So I'll show you an example of parameter sensitivity, but I'll take an example of, I have a stored procedure, it just got developed, and somebody jumps in and they use parameters for that stored procedure that are totally atypical. Like nobody's ever gonna use these parameter values. And they merrily test it, the plan gets cached, it's based on atypical parameters, and then everybody else comes in with the typical parameters, and it turns out it has a different data distribution, and performance suffers. That's one flavor of parameter sensitivity. And then out of model constructs, this is just a fancy way of saying there are things beyond the select star from where having group by relational world where we don't necessarily have a good technique or good visibility to the estimated number of rows. So we call them out of model, where either we're not handling them today, or they might have a level of complexity where they'll never be able to be adequately handled ever. Example I'll give for today is multi-statement table valued functions. So we have this construct of T-SQL functions that have been around for a long time. We'll talk about how they get used. I'll actually show you firsthand before 2017 what the behavior is of using them. And then the last thing is just assumptions. Let's say I have an order table again, and I'm selecting where state equals Minnesota and city equals Minneapolis. So I have 2 different clauses, 2 different predicates. You and I both know that city is correlated with state. Prior to, in an older version of cardinality estimation model, we did not know that in absence of multi-column statistics. So if you had multiple predicates against columns of the same table, another common example is make and model of a car. So VW Golf, 2 different columns, 2 different predicates. We assume in older versions that they're totally independent. So we underestimate the number of rows that are going to flow through because nobody's told us that these 2 columns are correlated, again, in absence of multi-column statistics. So these are the most common reasons. There's other more exotic reasons, but these are the ones that, over the years I've seen that are definitely the most frequent. And why should you care? All right, so I get a bad plan if I'm asking for too much or I'm asking for too little. Of course, the issue is performance. So query performance, your query performance, or other people's query performance. Excessive resource utilization, so I'm asking for too much CPU, memory, I/O. Spilling to disk, so I need, I only ask for 10 meg, I need 1 gig of RAM for my memory grant, and so now I have to actually spill to disk, which is significantly slower than had I asked for the right amount in the first place. Reduced throughput. Let's say you give me one gig of a memory grant for my request, and I only use 20 meg of it. Now, I'm running quickly, so I have no performance issue, but I have 20 other concurrent requests that are also asking for memory, and they have to now wait or be gated behind my request. So a very large request and a couple of concurrent requests doing that can cause unnatural gating. Nobody's using the memory, it's getting wasted, but your throughput suffers. All right, and it happens more often than not, actually. T-SQL refactoring. So this is the developer cost. I worked with one customer. They're a hedge fund. They put all their risk calculations in multi-statement table valued functions. There's the virtual functions. It's reusable. You can encapsulate that code. It's one place that I can go to modify business assumptions. But it is a black box leading up to 2017 from a query optimization perspective. Older versions, we assume 1 row flows from it. More recent versions, 100 rows. But what if you have 1,000,000 rows? All right. So into a description of what we introduced in 2017, and again, think of this as laying the base of different techniques that we've added to the engine. Rather than create a new set of assumptions, we're trying to actually adapt during runtime execution. So first issue, interleaved execution, or first feature, interleaved execution for MSTVFs. I know it's a mouthful. The problem I just described, if I'm selecting from a function, if I have millions of rows, we're still going to assume 1 row is flowing from that function. So if you're joining that function or performing lots of different operations, then the downstream side effect of that underestimate can be very painful. And I mentioned, once we have a plan, so I optimize and I execute, there's no going back. So if I say, whoa, I estimated 1 row, and I've already seen 1,000,000 rows flow through, we don't revise that plan prior to 2017. So interleaved execution is the first time we've broken that boundary between optimize and execute. What we will do for this first version is we will optimize up into the point that we see the function, and then we will go ahead and execute the MSTVF, which we were already doing. So we were already executing the function behind the scenes. We just weren't using the cardinality. We'll use the cardinality. We will re-enter optimization, and then downstream we will optimize based on the actual runtime count. Now there are other opportunities within the engine, things like table variables and other constructs that have the same fixed nature, and some of them are more applicable to being able to stop, get the count, and go. MSTVFs, we found it was a perfect conjunction of you have a lot of people still using them today, and they can be very problematic from a performance perspective. So that's one of the features we added, again, last year. Second one is memory grant feedback. So here's a problem, and it could go both ways. I'm overestimating how much memory I need. So I think I need 1 gig, and I use 20 meg. Or conversely, I didn't ask for enough, and now I'm spilling to disk. What we will do is we will learn based on executions. So if I execute, I spill to disk, we will register an event behind the scenes that says, oh, you spilled to disk. So for the consecutive execution, add memory. So second execution will add memory enough to cover the spill, plus a little bit of a buffer. If I'm wasting memory, more than 50%, we will go ahead and reduce that memory footprint and add a little bit of buffer for safety. and we'll learn over time. So if it needs a couple of adjustments, we'll do that. It can have consecutive executions. We can keep improving. Sometimes, and most often, we see it gets improved on the second execution. But this is the first time that we're learning and then actually feeding that in as part of the process. Question? Yeah.
Is this all turned on by default?
So the question is this all turned on by default? Thank you. So that is turned on under compatibility level 140, which is for 2017. And that's an absolute must-have because we've made this agreement that if you are upgrading, your plans should not regress due to any kind of scenario or improvement that we added. So there should be no plan regressions. And so we put in this compatibility level as that contract saying, hey, if you go to 140, you're opening your feature set up to these new features. Here, one thing, even stepping back even a little bit further, no matter what, because of the unique set of characteristics across customers, data sizes, schema variations, we expect most plans to improve, but there's always going to be a regression. It's always going to happen. And so we have to have that locked behind a compatibility level. So thank you for asking that. 140 is going to enable everything that we're talking about today. Now, if you create a new database in SQL DB today, the default is 140. If you have SQL Server 2017, the default is 140. And you can always bump it down if you have to wait for compatibility testing as well. So that's perfectly supportable. Okay. And then third feature, and then I'll show you demos. So adaptive joins. So, and you're going to notice each of these are at like different scopes. So the first example, interleaved execution, was within an actual optimization. So the first time I optimize, we can go in and out of optimization and execution. The second example, memory grant feedback, was for repeating workloads, learn. And this third is basically for at the operator level, adapt. Okay, so what operator are we talking about? If I have a low row flow estimate, so if I think a low number of rows are going to flow through a tree and you're joining tables, you have a couple of different algorithm choices. You have nested loop, you have hash join, you have merge join. In this example, you see two different trees that will have the semantic equivalent. One is with a hash match, one is with a nested loop. Nested loop is typically more of what you want to see for low row flow because there's a lower startup cost. Hash join is generally you're going to see it for bigger result sets. You have that startup cost for memory, but it could be much more optimal for large row sets. What if we're wrong? So if we estimate low and it's high or vice versa, then you can have an inappropriate join algorithm. So for the first time, we've added a one operator that behind the scenes is able to switch techniques during execution. Now keep in mind, this is one compiled plan and then one or more adaptive joins within your plan, depending on what you're doing, if you're joining a lot of different tables. But my executing a low row flow versus high row flow, same plan, we're not doing a new compilation for this. So what we will do is we will look at an intersection of costing. So if you look at the x-axis, you're going to see its rows. Y, you're going to see its cost. And notice, and on this screen it looks a little bit pink, notice the nested loop join. You see that it's, in terms of cost, on the y-axis, it's lower, the lower number of rows. So there's no startup cost. If I'm doing a nested loop, there's minimal memory required. I don't have to pre-grant it. But at a certain number of rows, it becomes more costly than a hash match alternative. You see this line where we have a higher, the hash match line, you see, or hash join line, you see there's a higher initial cost, but then it's less costly over time. That intersection, what we will do is, based on that particular plan and those particular tables, we'll look for that intersection, and that operator looks for the point where we reach that threshold. And then if we exceed the threshold, we'll do hash join operation. And if we don't exceed it, we'll use a nested loop operation. Again, the first time that we've had an operator that does it for the same cache plan switch strategies. Okay, I'm going to show a demo on this. Let's see here. I think am I 7? Here we go, I am. Okay. All right, so let's start with interleaved execution. How many folks have actually used multi-statement table valued functions before? Okay, all right. We see a lot of them out in the wild. Again, the virtue is understood. All right, so I'm going to start off in compatibility level 130. So this means that the AQP features will not be enabled. I'm going to show you our before state. And I'm going to include my actual execution plan so you can see what's happening behind the scenes. And I have this wide world importers DW database that I'll use. And just like with Shreya's examples, this is all on GitHub as well, equivalent demos. And I'm selecting from this fact order table, and I'm joining to my MSTVF, my function right here. And you notice it takes in a few input parameters. So this particular function basically says, based on an event, like a mild recession, show me what impact that would have had on order quantity. Like here was the before, and then here's the what if scenario. So I'm joining to it just like I would a table. And again, I'm including the actual execution plan. And this is the legacy behavior. All right, so we get the results back in about 3 seconds. And if you look here, even if you're not an expert at looking at query execution plans or you've never looked before, this is generally one of the areas that if you know the query that you need to tune, looking at an actual execution plan is absolutely critical. And one thing that stands out right away is I see little warning symbols by some of these operations. Okay, so if you see warning symbols, that's one big anti-pattern to immediately check out. And if I hover over this operator, we see, okay, the warning is operator used tempdb to spill. So my query, for whatever reason, spilled to disk. It didn't have enough memory to accommodate the number of rows that flowed through. Now, if I look at the actual output from what if outlier event quantity, that's the name of our function, and it's right here. I can hover over that operator, and you can see we talked about cardinality estimation. Estimated number of rows, 100. That's our fixed guess. Actual number of rows, 231,000. This has been the case since functions were introduced back in, 2005 maybe? I think it's been a long time. This has been the behavior. You won't notice it if you have a low row count, but when you start getting to larger and larger row counts and you start joining it to other operations, performance can suffer. All right, so that's our plan before. Now, what we're gonna do is just enable 140. And that's the only change I'm making. And just keep in mind that this will be the emphasis for this set of features and what we're going to be doing over the next year as well, where we just want to make things that make your existing code run faster. All right. So I'm going to rerun the query that I just ran before. Again, the only difference being that I'm in 140. And then if we look at the execution plan, you're going to see a totally different shape. All right, so operations got moved around because bigger tables should be on the probe side of a hash. So there's all kinds of reasons why you would want to do order of operations properly if you have several 100,000 rows versus just a few. And most importantly, just check this out. Notice there are no warnings. We didn't spill to disk. And if we look at the table scan for what if for our function, the estimated number of rows is 231,000. And the actual number of rows is 231,000. So again, that's just interleaved execution. You didn't have to do anything other than bump up the compatibility level, and yet it's important to be aware this is how this is working. This is why this is happening. All right, now let's show memory grant feedback. So I'm going to show a couple of examples. I'll show an example of wasted memory and one of spilling. So in this case, we're going to start off right away with 140. And I have this query from TPCH, and it's based on query 12, which is like a shipping modes and order priority query. And I'll include actual execution plan, and we'll just execute it. And I chose this one because it asked for too much memory. I know for a fact that if I hover over this select, I can see a warning down here. And I see grant size is a half a gig, that's in KB, but that's a half a gig. And used is 17 meg. So we're wasting a ton of memory. I've asked for too much. Now, you saw that query. It ran quickly, so no problem for me. But the time that you have a concurrent set of workloads and requests that are all trying to run similar queries, or they might all be overestimating what they need, all of a sudden you start gating. And I mentioned at the very beginning of this particular section, my two techniques when working with developers on performance tuning were weights and queues methodology and then cardinality estimation. Weights and queues methodology basically says if something is waiting on a resource, it is visible within SQL Server and SQLDB. You can see it. And so in this example, if I start gating, you'll see something called a resource semaphore wait. And so that's your symptom where you're like, I'm gating on memory. Now that could be a legitimate memory request. Maybe you really do need it and you need a bigger system or you need to rearrange. Or it could be, in this case, I didn't actually even use that memory and I can cause gating with other concurrent requests. All right, so given this, let's go ahead and execute. All right, and the warning symbol went away. All right, so that was my second execution. And if I look here, memory grant size, it's now 26 meg. What happened? I wasted more than 50% memory. We logged that internally. We said, you know what, if you execute this again, adjust the memory downward by the amount you were wasting, plus a little bit of a buffer for safety. So again, first time that we're introducing something that will learn based on execution count. This helps with repeating workloads. We also know there are a lot of scenarios where it's just one and done, it's only ever ad hoc, and this won't help you with the ad hoc, but it will help you with anything that's executed more than one time. All right? Now let's take a look at the spill scenario. So I'm going to use wide world importers DW, and again, under 140. And I'm going to do the classic parameter sensitivity scenario. So I have this store procedure. It takes an input parameter of lineage ID, and I'm using it as part of a predicate where I'm saying, okay, where lineage key equals this lineage key that I send in through the store procedure. All right, and I'm just joining a couple of tables, and that's the only thing I'm asking the end user to provide. So let's just make sure that this is created. And I'm going to do that scenario I just mentioned where I'm the tester. Somebody says, hey, could you test this before this goes live in production? And they go, sure. And let's say they have no idea about proper lineage keys. Like they think, I don't know what a good testing key should be, so I'm going to pick a key of 8. So they execute it, no rows flow back, but the tester says, you know what, looks good, it ran without error. Now, if you look at the execution plan, you're going to see little symptoms like this, like the skinny lines. That line thickness will show the row flow. So if it's skinny, we know that this was assuming a small number of rows are flowing through. But the problem is that if I execute with a representative, like a or I should just say a typical parameter value, it's going to run a long time, and its performance is going to suffer because that person who just tested it with parameter value 8 just caused that plan to be cached, and now it's sitting there just waiting for people to come in. But the problem is that plan does not represent the typical data distribution. So this is one variation of parameter sensitivity and parameter sniffing. So what are the consequences? Well, I ran it again with a good parameter, and I got back 231,000. Okay, so 231,000 rows. And if you look, we are just littered with warnings. Okay, so you're going to see we have a sort warning, we have a hash match warning. If you look at sort, you're going to see that the actual depth of that sort is quite high, so the number of times we had to go back to disk. So not only did we get it wrong, but we got it really wrong, and we're continually having to go back to disk to undo our misestimation. All right, so what do you do if I execute this store procedure a second time? Again, memory grant feedback kicked off behind the scenes. This time, I don't have any warnings. If you look at the memory, I've bumped it up appropriately. The plan shape itself was appropriate, but we just weren't asking for enough memory because of that bad plan that got cached. All right. And then last example for the AQP features. So I'm going to use the TPCH database again. And I'm going to base this query on query 18, which is large volume customer. And again, for adaptive join, just to remind you, the idea is we have one compiled plan. So the first time I'm going to execute this, I'm going to have a compiled plan that has an operator in it that can go with 2 different join strategies. All right, so we don't need to recompile in order to benefit from it. So if I execute, and I'll do it based on a value 314, which I happen to know returns 85 rows. And if I go to the execution plan, you're going to see this new operator. And a few things I want to point out. You have adaptive join is our operator instead of hash join or nested loop join. And also you have this outer branch. So this could be the driver of your nested loop or the build phase of your hash join. You have this second branch, which is your probe phase. Should we use a hash operation? And then you have this third branch that we use for nested loop. Should you use a nested loop operation? And in terms of visual indicators, you see thick lines, thin lines that give you an idea of row flow. But you don't have to count on those. You can actually just hover over the adaptive join, and you can see a few different key attributes I want to bring to your attention. So estimated join type. When we compiled, we estimated it would be nested loop. And when it ran, it should have been nested loop. So that's what we used. And why did we make that decision? Because we have an adaptive threshold rows. Remember that intersection of 2 join algorithms, the cost and the rows. That represents the intersection for this particular data set. And at 1,219 rows, if we exceed it, we go hash. If we go beneath it, we go nested loop. And if you look at actual number of rows, 599 rows are under that threshold. We use nested loop. Now, let's go ahead and execute on a parameter that's going to be far more in terms of number of rows. So again, we're not compiling a new plan here. We're not having to play any tricks around the actual mechanics of it or add hints. It's one plan accommodating two different algorithms from one operator. And if we look at the tree now, notice that this line is thicker. This is the build phase of a hash join operation. Now this nested loop inside is now skinny. However, if we go over adaptive join, this is an example where adaptive joins are beneficial because we estimated nested loop. We were wrong. We went with a hash match. And we were wrong because, our adaptive threshold is 1,200 rows. But our actual number of rows, 458,000. So we definitely wanted to change that algorithm. So any questions on this? Yeah. Yeah, so the question is, do we have merge hint? I mean, there's a merge join hint that I think has been around for a long time, but we didn't choose merge as an algorithm choice for this particular feature. Whether or not that gets on the roadmap, we'll see. We noticed most of the extreme examples were between those two worlds of nested loop and hash join. And with merge, typically from an optimizer perspective, if you've got, for example, pre-sorted inputs already, we're going to usually make a good decision around that. So it's based on what we were seeing for customer usage patterns on average. Yeah. Oh, so the question is, if you ran it with a query hints rule all. So if you go ahead and you put in that query hint, you're tying the hands of the optimizer. And that's actually one of the dangers of the query hints, because what might be a truth 10 years ago is no longer a truth today. And had the query hint not been put in, you could have leveraged something around AQP, for example. By the way, that is one of the markers. If I see a lot of hints sprinkled, I either am dealing with somebody who's very, very smart and knows their workload inside, or somebody who went to Stack Overflow, added a few things, it worked for that moment in time, but it wouldn't necessarily stand the test of time when data distributions change. Any other questions on this? Yeah, okay. You and then you, okay. Okay, so the question is basically, okay, I'll reframe it a little bit, and then if I didn't get the nature of it, stop on by and we can go through it. But can we do like a seek versus a scan adaptively? Is that what I'm hearing? So like, can you switch actual seeking strategies based on, like, one example would be if I say where product ID equals 10 and 1 million rows pass through, we would probably want to do a scan instead of a seek. And the answer is no, we don't have that today. It's an interesting space though, and there's a lot of different, what we're probably going to be focusing on are lower risk, higher reward. Certainly the seek versus scan is an interesting problem space that's been discussed. Okay, there was one more question. Yeah. Could you repeat that one more time? I'm sorry. So the execution pattern was showing, right? Yeah. Oh, okay, so the question is, and by the way, again, feel free to come back here as well if I misinterpreted, but does the query execution plan we're showing show realities around the characteristics of your storage, your CPU, and so on? It's a very good question because there's a lot of myths that have spawned over the years. When you see estimated CPU and estimated I/O in that execution plan, those are estimates based on a machine that's long gone. I mean, I think it's a machine from 1997. And that machine had specific assumptions. For example, here's how much a serial I/O is versus sequential I/O versus like a singleton lookup. And so we had these different costing functions, which at that moment in time meant something. Now they are a unitless measure. It does not mean that our costing is invalid because we're finding that the relative values are still important. But if somebody looks at CPU and says, oh, estimated CPU is 1.2, it doesn't mean anything. It just means that of the different costing alternatives, we chose the one that was cheapest based on the algorithms that were selected that you saw in that tree. Okay. All right, one more, and then we're going to go to Kevin.
How sensitive adaptive memory algorithm with high frequency needs of queries? Let's just say I have hundreds queries per second.
Yeah.
Some of them 40% require a lot of memory, 80% of little memory.
Yeah.
How it will jump back and
Good, great question. Okay, so the question is, I have an oscillating scenario. Sometimes my input parameter is 1 row, sometimes it's 1 million, it returns 1 million, so there's no right, it's truly the canonical parameter sensitivity where no one size fits all. In that scenario, we will disable behind the scenes. So if there's too much oscillation, we will disable it. Right now, in terms of visibility, you can see that with an X event, but after a certain number, we will stop doing memory grant feedback. If we go up and down, then we stop, okay? All right, so we're gonna move to Kevin now.
All right. So I'm going to talk a bit about automatic tuning. We're starting to move into the realm of what we're calling intelligent query processing. So Joe has been talking about adaptive query processing, where we're adapting what we do based on what we see during execution. We realized that there's another whole set of strategies we could use that weren't really adapting to anything, but they're making the query processor smarter. And again, the overriding theme to all this is we're looking at ways to make things just go faster. So to take the work off you guys, so you upgrade and things just go faster and smoother. That's the goal here. So with automatic tuning, who's familiar with the query store? So query store is the flight data recorder for queries. What it does is it tracks for a given query hash. So the text of the query has a unique hash. For that query hash, we track different plans that are compiled over time and the performance of the various plans. So you can go into a UI and say, okay, for query number 45, or the query with this text, we had this plan and that plan. That plan was slow, this plan was fast, whatever. So what automatic tuning is doing is it's taking advantage of that and taking that a step further. So queries get recompiled for a lot of reasons, different parameters. Parameter sniffing is a classic. The new plan might not be optimal for the general case. That was the example that Joe showed. Overall performance can degrade abruptly if you get the wrong plan compiled. And it can take time to figure out what went wrong. So the solution is that the query store has all the information we need to fix that, because it can tell you, okay, for this query we had 2 plans, and the plan you're using right now takes 10 times the CPU of that other plan. So it gives you the ability to go in there and force the plan that was faster. So that's a huge benefit, but we can do better. So what automatic tuning does is it takes that whole analysis and tuning operation and automates it. So the idea is that you have a performance problem, and we're going to be able to automatically tune it or fix the performance problem without you doing any tuning. And again, this runs in 3 different modes. It can run, you can turn it all off, disable query store, do everything like you've been doing for the last 20 years. Or you can turn on the query store without any automatic tuning enabled. What that does is it'll tell you, okay, we've had the performance problem came in, you've had a regression because of a new query plan. What this bar graph is showing the speed of the query, or the execution time. And so with automatic query tuning, so the query store will then tell you, you've had a regression, this is what I think was the problem. And with automatic query tuning, you can get a recommendation that says, this is the problem, you had a regression, this is the problem, and it'll give you a snippet of script to correct it. So you can correct it by running this piece of script. Once you gain confidence in that, you can turn on a switch that says, automatically force the last known good plan. So if there's a plan change that got worse, find the last plan that was good and force that to be the plan that's used. So again, you have execution going along happily, and suddenly it regresses. The red bars indicate that your execution time shot way up. Force last good plan equals on is the syntax for forcing it. It can be helpful for parameter sniffing situations. You have DMDB tuning recommendations, puts out a JSON bundle that tells you what went wrong. Automatic tuning, the system just corrects. So let's see what that looks like. So you'll see this looks like a little bit different UI than you're used to. This is SQL Operations Studio, which is a new UI. I'm using it because it presents a really good way to chart results over time, which just makes a good visual for this particular demonstration. This demo uses the Wide World Importers database again. What we've got is one script called report, and that just runs a report query in a loop using a particular parameter. So it's a parameterized report. We're using the number 7. We have batch request perf collector. What that does is it looks at the perf counter object for batch requests per second and just caches them with a timestamp in a temp table. So that just spins in a loop, collecting how many batch requests per second we're able to run. And then there's batch requests is the query that pulls that temp table and gets you the results. We have a regression script which introduces a regression by using parameter sniffing. So we clear the procedure cache, execute with a non-typical parameter, and then when we go back to the report query, suddenly you've got a compiled plan that's the wrong one. So let's see what that looks like. So we're going to start up the report query. So that's going to start running. That's spinning. Start up the batch request perf collector. That starts running. Let that settle for a little bit and execute the batch requests. We can look at that as various different kinds of charts. Oh, come on. So it's a time series. That's what it looks like. So we've got a performance level established. I'm going to cause a regression. And again, all this is up in GitHub, so you'll be able to look at it. We'll see what the regression script did to our performance. So we run that again, visualize it as a time series. That was not it. Okay. Scatter. There. Okay, let me hit the regression script. Okay, so you see the performance drop off a cliff. Something bad happened. How many of you have ever had a production system suddenly tank performance? How many of you had it happen in the middle of the night? This makes for a bad night. So at this point, phones are going to start ringing. People get woke up. You got to figure out what happened. People are not happy. So we have a script here that will look at the recommendations. So this is the recommendation DMV. So you have what happened. The average CPU time changed from 78 milliseconds to 309 milliseconds. That might be a problem. State transition reason is that automatic tuning options not enabled. And the script to fix it is to force the right query plan. So if we go out here and turn on, oh, come on. Okay, kill that one. I'm going to start everything over here. Stop the report query. Stop the perf collector. an initialization script that just resets everything to the state it was in. That's interesting. Okay. There we go. Okay, I should have cached. I don't know what happened. There we go. Okay, now we've reset everything. Start up the workload. Start up the perf collector. Look at our performance levels. So that's left over. We'll rerun this. Make this a time series. So we've only got a few data points at this point, but you can see about the performance level we're getting. We're going to turn on auto-tuning here. So this just sets that parameter that we saw before. So now when we hit this regression, we should fix ourselves. Okay, so we just hit a regression. We're going to look at the performance levels. Right? So you saw it fall off a cliff, and we forced the last known good plan, and it comes right back up. And in this demo, it takes about 10 seconds between the time the performance fell off a cliff until we recognize that there was an issue, that there's a way we can fix it by forcing a good plan, and apply that fix. So 10 seconds, it's not enough time to even ring the phone and wake anybody up, let alone having to deal with it. You'll see the log in the morning that said, oh, there was a blip during the night, and you can investigate it or not. But the main thing is nobody gets woken up in the middle of the night. So this is why I really like this feature. So beyond 2017, what's happening? As Joe mentioned, we have features in development all the time that are going beyond adaptive query processing. We're looking at all the reasons that we have performance problems. So constructs that the optimizer isn't able to accurately estimate, and looking at ways we can make that perform correctly so the optimizer gets a good view. Lots of different strategies we're working on. We will be introducing them in Azure SQL Database as they're available. So as soon as they come out in a public preview in Azure SQL Database, we'll blog about it. So you can read about it there and go experience them. And then they'll be in the next iteration of SQL Server on-premise when that ships.
When does it get shipped to Azure?
So we release bits into Azure about once a month. So the first stage that'll happen is that we'll put it into a public preview where we'll announce it, but it's not to be used for production yet. And let people get experience with it. Let us find out if anything goes wrong. When we're confident, we'll make it GA, which means you're OK to use it in production. And watch this space. So blogs.msdn.com SQL Server Storage Engine is the blog that the SQL Engine team, which is generic to SQL Server, Azure SQL Database. It's all the same source code. So at this level, there's no distinction between the two engines. So this is where the team blogs. This is where you'll see our announcements when we light up new features. Any questions?
How does the engine react to the lack of, for example, missing non-cluster indexes?
So missing non-clustered indexes. On-premise, you'll get a warning. With Azure SQL Database, there's some additional machine learning that can kick in that can actually give you a more fine-grained idea. And if you turn it into automatic mode, it'll create the index. for you on the fly, and it'll continue to monitor performance. And if it understands from continuing to monitor that that change didn't help things, it'll back that index back out, so you don't have to maintain it.
And by the way, on the next 2 slides, you'll get this with the deck. We have graph recommended links, so if you want to follow through, and also intelligent QP, adaptive QP. Okay, there was a question over here. Yeah.
With Azure SQL database, who owns the responsibility of maintenance of indexes, et cetera?
So the question is, for Azure SQL Database, who owns the responsibility of maintaining indexes? And actually, this is very timely. I had this question at a booth. When we were talking about automatic tuning, that's talking about creating indexes. It's talking about dropping indexes. It is not maintaining those indexes for you. Now, with that said, you want to be smart. You don't want to just rebuild a bunch of indexes every single day because you think that it might be helpful. You don't want to use up your Azure SQL DB resources unnecessarily. So my recommendation is take a look at the entropy for that particular index or workloads that use that index. And if you see that there's a lot of fragmentation, and then that leads to higher I/O operations, so you're consuming more I/O, certainly adding your own maintenance job would be good. Now, if we jumped in and we did it on your behalf, it would probably be inappropriate because there are some scenarios where your indexes should be left alone. There are some scenarios where the fragmentation does not matter. So it's still in the realm of something that you choose to apply, but I would just say do so intelligently. Do so with looking at DMVs and actual runtime characteristics and then history, and not just indiscriminately updating everything. Okay? And any other question? We'll take one more, and then anything else you guys can come up to the stage. I saw one here, and then bonus question there. All right.
So what is used as a measuring stick on that graph to detect the drop in performance? Is it query cost? Is it execution time?
So the axis on that graph that I showed in the demo was batch requests per second. So it's the level of performance. How many batches can we get in per second? That was the vertical axis. The horizontal axis was time.
So it's not based on particular query, but it's the overall count of the SQL instance?
So this was how fast are we able to run this report?
Yeah, it was the CPU characteristics associated with that request execution. And we track that. So it's looking at whether there was a time difference between those two, between the prior and the current
So
running average.
since it was serial execution, the less time each execution takes, the more we get in per second.
Okay, well, there was one bonus question, then we'll be done.
Yeah, I was kind of wondering, Shreya mentioned with the graph database for the hierarchical bill of materials scenario. I was kind of wondering, what's the advantage of the performance advantages there, or is it just easier to query versus just using a recursive CTE?
So there are some performance optimizations that we have introduced for graph feature, particularly if your match pattern is very long. The ones that I showed were very short, just so that it's easy to understand. But if they are very long, and the pattern can be as long as you want, we introduce certain optimizations there. So let's say if you are searching through a deep hierarchy, your match pattern will be very long, and there you get some implicit optimizations that we have introduced. So your queries in those cases will definitely run faster than equivalent relational query. And besides that, for the next version, we are introducing certain features which will have some built-in optimizations for graph queries. So there you'll benefit. So if you adopt it now, you're going to get it in future too.
So please complete evals. That's how we learn. That's how we get better as speakers and present an even better session the next time.
Thank you.
Thanks.